Struggling to solve for integrals nowadays, and they involve both a numerator and a denominator? Well, have no more fear. There's been a new product that we are here to introduce to you called Integration by Partial Fractions. And it helps you solve your most complicated integrals that, again, involve a numerator and a denominator. So now we're going to continue on and show you how to use this brand new product brought to you by Megs, Aaron, and Sam. Integration by partial fractions, the intro. Now your denominator has to be able to factor out into something. That's going to be step one. So how to do that? You have 1 over, let's see, we have x squared minus 7x plus 10. So then you would have x minus 5, and not negative x minus 2. So that would be what you would factor it out to be. What you want to end up doing then is splitting it up. So then you would have your integral of 1 over x minus 5 plus your integral, because you're splitting the integral in half, so you need to have integrals on both parts. And your integral of 1 over x minus 2. Then you want to have constants on top, so change your 1's into a and b. That's how you start off your partial fractions for integration. Now I got rid of the integral signs because it's easier to assume that we are all taking the integral of all of these. So then what you want to do is you want to multiply everything by your denominators. I'm going to put these into brackets. And you're going to want to multiply it by x minus 5 and x minus 2 all over 1. So then what you end up getting is this. A times x minus 2 plus b times x minus 5 is equal to 1. Because over here, everything canceled out. So then you're just left with 1. What you also want to remember is that you have other variables on this side. It's just not being shown because it's multiplied by 0. So how you can rewrite this is just 0x plus 1. So then you would have 0 plus x plus 1 is equal to a times x minus 2 plus b times x minus 5. Now I kind of got to erase all this so I got more room to write, so give me a minute. We've multiplied it all out. Wow, I'm a little behind. So then you have ax minus 2a plus bx minus 5b. So then that's when you take out all of your common variables. So then you would have a plus b times x plus minus negative 2a minus 5b. Now, this is again all equal to 0x plus 1. So then if these have to equal each other, so then a plus b would have to equal 0. And then negative 2a minus 5b would have to equal 1. So now you actually have a system of equations. You have a plus b equals 0. And you have negative 2a minus 5b equals 1. So then what you can do is you can multiply this top one by 2. So then you would have 2a plus 2b still equals 0 because 2 times 0 is 0. So then what you want to do is you want to add all the terms together. So you have this system of equations, right? So I'm just going to solve this for you, even though I can pretty much assume that everybody knows how to do systems of equations at this point. What you wind up getting, negative 2a plus 2a, just equals 0. So you have 0a, and then negative 5b plus 2b is equal to minus 3b, and then 1 plus 0 is still equal to 1. So then you have to solve for your b value. You divide each side by negative 3, giving you b equals negative 1/3. There's my work to show you. So then to solve for a, you can plug it into your a plus b equals 0 equation. That's the word I'm looking for. So then if you have a plus b equals 0 and b equals negative 1/3 equals 0, so then you add 1/3 to each side, giving you a equals 1/3. So then what you want to do to get back to the partial fractions, you take back to your integrals where you have x minus 5 plus the integral of b over x minus 2. Okay? So what we're going to do is we're going to simply erase these variables and plug in our values. So a equaled 1/3, and then b equals negative 1/3. So then you can look at these integrals and you can solve for those integrals. They're going to be a lot easier to solve for. That, my friends, is integration by partial fractions. A little bit more complicated.
As you can see, we have an unfactored polynomial on top and a factored polynomial on the bottom. And even though they're not from the same polynomial, they have like terms, which will help us solve with partial fractions. So as you can see, we have an x squared on the bottom and on the top. So when we make our fractions, instead of it just being a over a fraction, we're going to have ax plus b over our factored polynomial. And then for the next one, we're going to have a c over our other one, since we're just going down the line of the alphabet as we add more fractions. So then for the next step, you want to multiply your fractions by your denominator. So, and you have so, as in the problem before, like Meg, these two are going to cancel out since they're like terms, and same with these guys. So you're going to end up with this equation, which is going to equal your numerator, the unfactored polynomial. From there, you're going to want to add your like terms. So like I said, add your like terms, and that's going to equal your unfactored polynomial. From this point, then you're going to want to make your systems of equations. So you're going to find your x squared. So you have an ax squared, a cx squared, and then on the left side you have a 2x squared. So you want to put those equal together to get your first systems of equations. So you're going to have like that. So from there you can divide this whole thing by x squared to get rid of your x squareds completely in your first systems of equations. So you'll be end with a plus c equals 2. From here, then you're going to go on to your next system of equations. Since you have 1, but you still have the rest of your equation unsolved for, so you got to solve for that as well. So you have 1, 2, and 3 systems of equations. And then from there you're going to want to solve for your equations. So for 1, we can assume that a plus c equals 2, so we can assume that a is 1, c is 1, which equals 2. And then from there, we can plug in 1 for a, so we have b minus 2 equals negative 1, bring that over, and b equals 1 as well. And there we can plug b and c for 1, so we have c minus 2 equals negative 1, which is just -1. For the last part, you're going to want to plug in all of your variables for the equation. So you're going to have the first integral, so then those are going to be your 3 integrals, and then you'll solve from there. Then you'll solve your integrals because these integrals are going to be a lot simpler to take the integral than what we originally started with.
The unsolvable.
Okay, so then if we follow the same process, for example, an integral of 1 over x minus 2, x minus 1 dx, you're going to get something a little bit different. So basically, from here, you're going to have your a over x minus 2 plus b over x minus 1, just like we did in all the other equations. But from there, you're going to do the exact same thing and solve it out. You're going to have 1 equals a times x minus 1 plus b times x minus 2. We did the same process where we multiplied both the denominators through, so we're left with the opposite denominator for each a and b. So from here, when we put it together, we get 1 equals a plus b x plus a negative a minus 2b. And from here, when you solve out your systems of equations, you're going to get a plus 2b equals 0, and you're also going to get a negative a plus 2b equals 1. But if you solve this through, you're going to get 0 equals 1, which in this case you aren't able to solve this function using partial fractions. So unfortunately, you'd have to use a different method or something else that we know how to do that we can solve for this one.